recording here, and it is now officially 6:15 by AT&T's clock. So I will start. All right. Today we're going to talk about memory corruption and exploitation, particularly on Windows. And I just wanted to get an idea of where people's experience is so far, so I'm kind of talking to about the right level. First, how many of you found the bug in the homework that found the vulnerability in the homework.exe that was assigned, like I think last week? Is everyone, or just like the three of you that are raising your hand? All right. So that'll make this a lot more difficult. But how many of you have written like a local exploit before, like a basic like Stack Overflow? All right. And also, I'm going to let you know that I'm going to call on you randomly for things, and I'll refer to you by the brand of laptop that you use. So by keeping a laptop open, you are increasing the chances that that I will call on you. So I hope you're taking notes on it and not doing anything not as useful. Just because I want to make sure that people are paying attention, because the thing with exploitation is this is hard. This is not like, we're corrupting memory, we're changing bytes, and we need to, keep you aware of what's going on. And I'm going to move through things kind of quickly, and I guarantee that I will forget to tell you something very important. And you will only realize this when you're doing your homework the night before, 3 weeks later. Yeah, you guys should try and watch what's going on here. And if anything's unclear, don't be shy, raise your hand. You're like, I have no clue what you did just there. So like, is everyone following what I'm doing on the screen right now? All right, we're good? Okay, just wait 5 minutes. All right, so I'm talking about memory corruption. And what this is this is a broad class of vulnerabilities that refuses to die. And I kind of tell you a little bit about what I mean by memory corruption. It's when there's a programming error in the application and it causes the program to access memory in an invalid way, and that results in undefined behavior. And so before, people considered these just bugs. It would cause the program to crash, and things were undefined, and ooh, that was weird, and then you run it again, and it does something different. But as attackers, what we try and figure out how to do is turn that undefined behavior into defined malicious behavior, like giving us a shell. And there's a variety of ways that memory corruption can eventually result in this. So if you have a way to corrupt memory and that overwrites memory, you might be able to change the value of a variable in kind of an undefined way. You can also overwrite memory that's reserved for the programming language runtime, or that the compiler uses for something special, like a return address. If you overwrite that, bad things happen. Also, memory corruption kind of includes not just changing memory, but also reading memory at the wrong time. So kind of the latest hotness in browser exploitation these days are what are called use after free vulnerabilities. And these are essentially just reading memory after the memory's been freed. So you're not changing it, you're just reading the memory at the wrong time. And you can turn this into code execution. And this slide is, I need to shrink the font. But this is a vulnerability when memory corruption will allow an attacker to gain increased privileges or capabilities, or against a remote system or a local privileged system. So there's a variety of subclasses of this. There's the classic buffer overflow, and for some reason we need to give them names depending on different names depending on what actual data gets overflowed. So you can overflow data on the stack, you can overflow data on the heap and the data segment. Anywhere you can store data, you can overflow data. For a brief period in time, there were these things called format string vulnerabilities. These were quickly found and eradicated pretty quickly, but they were a lot of fun. Where you could, how many of you guys know C? All right, okay. Actually, more than last year. So yeah, if you know how to use printf, if you can, control the arguments to printf, you can do cool things. Like you can print out a bunch, if like someone builds a string to printf from data that you control, you can say, all right, I'm going to print out, %x, 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 %x. All of a sudden, the program dumps out the entire stack into, standard out. So for instance, I found a vulnerability a long time ago. There was a format string bug in a web server. And so what I could do is I could send a request to it, and it would have, part of the request would get into a format string. And so I could, do a bunch of %x's And then I had another bug where I could access the error log of the server, and then I could look at it, and I would see all the stack memory from the process. And so I could use that to, then there's other tricks you can do with format strings to actually corrupt memory. And so in this case, what I could do is I could look at that stack memory, make sure everything was where I expected it to be, or recalculate things as needed, so that when I actually ran the exploit and corrupted memory, I was precise and correct 100% of the time. So format string bugs are also really cool. You can also get this from out-of-bounds array access, like if they're not checking the indices of an array, and you can access before or after the bounds of the allocated array, you can corrupt memory. Typically, integer overflows are kind of talked about with memory corruption because an integer overflow typically leads to another type of memory corruption. So if you overflow an integer and that's like used as a length or something like that, you'll pretty soon get out-of-bounds access. And uninitialized memory, dangling stale pointers, use set to freeze. These are all kind of subclasses of this. And usually what we want to do with this is, okay, so we can corrupt memory. If you're not careful, all you do is make the program crash. And that's not all that useful to us as attackers. What we'd like is we'd like it to give us something that we don't have. And I may not currently have a shell on that system, but I would like that system to give me one. So what we do is we try and get it to run our shellcode. And the shellcode is what we usually call just a small bit of machine code that we inject into the process and get it to run it. So we corrupt memory and hijack execution flow and make it execute some injected code that we have put there. We call it shellcode because it usually gives us a shell, but it can really do anything. So, for instance, it can, like if you use some of the fancy Metasploit payloads, what it'll do is it'll install a VNC server, in memory and let you just VNC into the server and have full graphical control. Or I wrote a payload for macOS 10 a few years ago. They would take a picture of the user from their camera and upload it to me. That's weird. I say macOS 10, and Charlie Miller calls me on the phone. It happens all the time. So yeah, you won't always run a shell, but sometimes that's usually what you want to do because it'll give you interactive control. You can use that to get more privileges on the system and so on. But one of the things you need to keep in mind is that not all memory corruption exploits execute shellcode. That's just what happens 90% of the time, but there's no guarantee that it needs to actually run either a shell or even run executable payload. Like it could not actually run arbitrary bytes, and you could still take advantage of memory corruption. So here's an example of that. These are a little more rare, but really cool. So this is a bug from probably before a lot of you were born. That was in Solaris up to Solaris 8. Everyone knows what Solaris is, right? All right, a few of us. All right, so back in the day before all Unixes were free, there were Unixes that were not free, and Solaris was one of the popular ones, made by Sun, now bought by Oracle, and ran on big expensive servers. But they had an awesome vulnerability that worked like this. So you would have to magically set some telnet environment variable called tty prompt to anything, and then you would connect to remote server. And instead of giving you the login prompt, it would just give you an empty string, and then you'd log in as a user, like bin. Bin is an internal user that's always on the system, and then space something, space something, space something, space something. You do a bunch of these space somethings, and all of a sudden, if you did the right number of them, it wouldn't ask you for the password. As you can see on the output there, I typed in bin space C space C space C blah 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 blah. Hit enter, and it just logs me in. Never did ask me for the password. So, and you can see I typed who am I, and it says you're bin. So obviously there's something really crazy going on here. And this is where I will start asking people with laptops to explain what they think is going on. All right, Mr. Asus.
I guess this would be considered this is memory corruption.
It is memory corruption, but how, what do you think is going on behind the scenes here? How did this happen?
Overflowing the stack, so.
Well, if I overflowed the stack, what would happen is basically you would probably hit a return address if I overflowed enough of the stack, and then it would try and return somewhere weird and crash. But it doesn't crash. So it's probably not overflowing the stack. All right. Let's see. Who has a Dell? You have a Dell. Do you have any? Oh, he has a Dell too. All right. Well, I can see the brand of your laptop. So let's. What do you think is going on here? Either of the Dells. So far, Asus is winning because they at least tried.
Maybe it runs another code somewhere else to go to authentication.
You think maybe there's like some extra code that says like, do authentication. It's somehow jumping there. It's kind of taking a shortcut. Yeah. It's getting close. All right, do you have a?
Are you writing past where the authentication check is done?
Well, how are you writing past it? Like you're writing over the code that. Okay, you're closer. All right, let's try someone with a Mac. All right, you're right here.
Well, you said it wasn't overflowing the stack, so is it overflowing the heap or something?
If I recall, I think it is. Or actually, no, it's not. It's not overflowing the heap. No, sorry.
Well, that's probably an exact number, or exact amount of the size of the string. So that's getting written somewhere, and it's probably stopping over the like someone was saying stepping over the authentication part of this function and just going straight to past that and just giving you a login access.
Closer.
Is it maybe writing over one of the function parameters with a space that's critical to some sort of security check?
Close. That's kind of the right idea. You're thinking outside the box here.
But it's like, isn't the buffers grow upward, right? Is that right?
Yeah, on the stack they do. Anyone else want to take a stab? All right. So this is actually a really awesome vulnerability because this just happened. Like the planets happen to align so that buffer, memory allocate or memory buffers in the data segment. So this is an overflow in the data segment. So this is static data. It gets compiled in. It's not like the heap that grows dynamically. It's fixed size. So on System 5 Unixes, you could log in as a username, space, and then specify environment variables. And then so once you logged in, it would send those variables to your shell. So for instance, if you want to log in as Dino space capital home equals /tmp, it would move my home directory to /tmp after I logged in. So in the code that parse this, it would keep tokenizing the input and assuming each of these is a variable equals value pair, and then put those in an array. But they didn't check to make sure that they didn't run off the top of that array. And so this array was fixed size in the data segment. And so they would keep filling things into the array, and then just after the array ended, they would keep writing pointers into memory to these strings as you went down. So and it just happened that one of the variables in the data segment following this array was a flag that basically meant is the user already put in their password. So basically it's initialized to 0. Well, once you override it with a pointer to some string, it's non-zero, which means that it's interpreted as true. So then it overwrote that value or that variable, and then once the code ran that said, hey, has the user entered their password already? If they haven't, I should ask them for it. It says, oh, they have entered their password. Well, I'll just give them a shell now. And so it's just kind of the planets magically aligned and did this. One of the interesting things about this is there were a number of different exploits for this same vulnerability. Some of them actually tried to inject shellcode and get it to run, it was very difficult because you'd overflow the data segment, and the stuff you could overwrite was not very easy to use. But obviously, if you just did this, it was trivial to use. So it just shows for the same vulnerability, you can do two wildly different things. One that gives you a horribly unreliable exploit that will just never work and take you months of your life, and another one that will work 100% reliably out of the box. And if you do this in front of someone, which I actually did a long time ago on a penetration test, where it was like one of those things where I had to have someone over my shoulder and I had to ask them permission to break into a system. I'd say, hey, I'd like to break into this server, and they're like, okay. And so I just typed this up and then logged in, And the look on their face was like I had just said, "Permission to walk through the wall, sir." And they're like, "Okay." And I went, so yeah, this is one of my favorite bugs of all time. So yeah, so I mentioned earlier that memory corruption is one of those bug classes that refuses to die. Everyone keeps saying, "Oh, this problem will get fixed soon. We'll have type-safe programming languages, and we'll have ASLR, and we'll have this, and then we don't have to worry about these type of attacks." Well, we've had type-safe languages since the 60s. You know, like Lisp was type-safe, and it doesn't have any of these problems, but we never used it. So we kept building systems with other languages, and so this problem persisted. And then, then we had another defense, and then another attack. And so here are some I list some milestones that I find personally interesting. I think the first public mention you can see of exploiting memory corruption is this Air Force report on testing the Multics operating system to see whether it's like safe enough to use for multiple levels of classification. And one of the kernel vulnerabilities they discover is something that lets them, write arbitrary values to a piece of protected memory, and they say, oh, we can exploit this vulnerability to do this, this, and this. And so it's pretty much the same as what you do like on a kernel exploit these days. But that was kind of no one really paid attention to it and kind of forgotten about it until the Morris worm hit. And one of the things, the Morris worm would guess passwords, and it would also use a sendmail backdoor. But one of the other things it did was it used a remote stack buffer overflow in the finger service against VAXs running BSD. And that was the buffer overflow exploits, kind of their big party, because it took down the internet. And everyone's like, it took down the internet because it kept crashing a lot of services too, and just keep reinfecting. But if you look at the decompilation of the Morris worm and you actually look at the exploit, it is virtually identical in the formula that we're going to do today, and also that was in Smashing the Stack for Fun and Profit by Aleph One from 1996. That's the paper that a lot of people cite as kind of the first big buffer overflow paper, but I mean, really, like 8 years ago, Robert Morris had it spot on. He had the NOPS, he had the machine code that executed execve. I mean, it's identical. But the funny thing is, between that period of time, people kind of forgot about it again, because on BugTrack, kind of one of the big mailing lists back then, this guy Thomas Lopatic found a vulnerability in NCSA HTTPD, which is kind of the precursor to Apache, and was like, hey, I think I can overwrite the return address, and if I can do that, I think I can point it back into the data that I uploaded, and then it runs it. That's crazy. Check this out. And everyone's like, holy crap, I didn't know you could do that. And so, but the worm obviously did the exact same thing, so they kind of forgot about it. But then started the period of everyone kind of on the defense side assuming that every type of exploitable memory corruption issue was a special case, or it was like the only type, because people at first thought that stack buffer overflows were the only problem. They're like, oh, as long as we can protect return addresses, we'll be fine. And so here's what another thing we can do is we'll make the stack non-executable. So when you write data onto the stack and try and return back to the stack, it's not going to run. So for instance, there was a mode you could run Solaris machines in that would do that, and there were patches for Linux to do all that. And then Solar Designer got around that. He's talked about, this is when he posted to BugTrack and kind of coined the technique called ret to libc, or return to libc. And he's like, oh, actually, we can just do other stuff. And then look, we can still exploit. We can still run code. And then people said, all right, we'll just make sure that we get rid of all stack overflows. And then there were, people don't really think about how to exploit overflows of data on the heap until Solar Designer also came back and made a post saying, hey, there's this heap buffer overflow vulnerability. And I found out that, heap blocks are stored in a way that if you overwrite a unused heap block, when it's pulled off the free list, I can write a chosen value to a chosen location. And then I can do this and this and this and get code execution. So people are like, holy crap, heap buffer overflows are now exploitable. And so on for at least another 10 years. And that's just kind of how it continues today, where basically now we'll say, all right, we fixed the problem, we fixed ASLR. So ASLR fixes a lot of things. And I'll talk more about these mitigations like ASLR, because if I say ASLR, how many of you know what I'm talking about? Like about a third. So ASLR is address space layout randomization, and it's one of the defenses that was designed to stop a lot of exploitation. It's actually a very good one. It makes a lot of things more difficult, but not impossible. So it's just, you just kind of keep figuring out more ways around it. And I'll talk a little more about that later. But the two big mitigations that people talk about are non-executable memory. On Windows, this is called data execution prevention, and ASLR, which moves everything around, which is on a lot of operating systems. So that's what memory corruption is. But we want to figure out, first we want to analyze a vulnerability, like that caused the program to crash, and figure out if we can turn this into an exploit. So that's kind of the vulnerability analysis phase. So if you can if a program crashes, there's a couple things you want to know. One, is it repeatable? Can you send the same input and have it crash in the same way? Or reproducible. Also, can you do things to make it more reproducible or more repeatable? Sometimes with multiple threads, with different systems, a lot of things like where heap blocks are allocated will change, and so vulnerabilities will be difficult to reproduce in the same way every time. But when we're doing kind of the vulnerability analysis, well, I'll kind of tell you a little bit about how to do that. You'll see how we can make it more reliable and kind of do the same thing every time, which is something that we need in order to reliably exploit it. Also, when you're corrupting memory, can you control what memory gets corrupted, like what memory gets changed, and how it gets changed? Can you control the values that get overwritten into something, or do you have no control over, the value? For instance, is the vulnerability something that lets you write a 0 to a chosen memory address, or just writes a bit somewhere randomly? Those things will be very difficult to control. But what we're going to play with today is just a Stack Overflow, which is just, something that writes data that you control all over the stack. Pretty easy to control. And in order to help you kind of figure out whether something is exploitable, there are a couple tools that will help you on different systems. One that I'm going to show you is called Bang Exploitable, which, have you guys covered this in class already? Microsoft's Bang Exploitable? All right, so I'll tell you what it is. It's basically a tool that runs in the debugger and tries to give you some idea of whether a crash might be exploitable or not. And it's very imperfect because it's operating after memory's been changed and all this stuff, and it really doesn't have a full picture. But for a lot of the easy cases, it can say, yes, this is definitely exploitable. If it says it's exploitable, it most likely is. If it says it's not exploitable, it might be. And if it says it's maybe exploitable, it's still a gray area. But it's still useful, and it can kind of help you understand a vulnerability a little faster. There's a similar tool for Mac OS X called Crash Wrangler that you can get if you're playing around there. So in the process of exploit development, there's kind of a few stages that we're going to go through. The first stage is we're going to try and, if applicable, make sure that we can reliably cause the same memory corruption. And we're going to figure out how to control it. We want to control how much data we write. We want to control what data we write. We want to control the execution state of the program so we know what we're overwriting. All these things are kind of some people like it, some people hate it, the fun part of exploit development, trying to get the program to do what you want. And then once we can corrupt memory in a certain particular way, or we figure out the universe of options we can do, we can figure out all the memory overwriting capabilities we have. We figure out how to leverage that to change the program's behavior to give us more privileges or more access. And that's kind of the heart of memory corruption there, is taking a little bit and a little bit of corruption and just expanding it until you have a shell or you have, cool stuff. And usually we want to make it execute our payload, because it's nice to be able to have kind of a separation of the exploit from the payload, where we can just write our exploit payload in assembly code, and then we can use it with different exploits, and we don't have to change it. So that's kind of the generic way of doing things. And if you do it right, you get a remote shell. And if you're lucky, you get remote root or remote system, and you can do whatever you want to the remote host, and that's fun. How many of you have ever used an exploit like this to break into another system? All right. How many of you have done that with the owner's permission? Okay, yeah. Oh, okay, yeah. So actually, that's what we'll do next week. We'll use.
We didn't write our own
scripts.
Okay. So I think so. What we're going to do for this one is we're going to write our own remote exploit, and then next week I think the homework is actually turning that into a Metasploit module, so you can use their payloads with your exploit, and show you how to do that. So all of a sudden you can use it to, get a full, like use an interpreter or get like a full VNC session to the remote system. All right, so let's kind of talk about the easy case first, which is the stack buffer overflow, which the funny thing about these is that they're ancient, but they are still exploitable on many systems today, and you still find these type of vulnerabilities. You still find just unchecked string copies, and they weren't compiled with the latest compilers, so that you can still use this stuff. Or it'll be on a on a smaller, maybe embedded system, where they don't have the kind of the advanced memory protections that your desktop or your laptop or even your phone does. So let's talk about these basic ones. So I'm sure you've all seen way too many stack diagrams, but I think every presentation on exploitation has to have one. And this one has the really, really bad one I made a long time ago. But basic idea is stack memory grows downward, and as you enter a new function and so on, and enter a new function frame. Actually, how many people are familiar with, like stack frames on the stack? Are people we're kind of loose on that? All right, so can someone tell me why we actually have stack frames on the stack? Like, what were they designed to enable? All right, go ahead.
They were designed to allow each individual function to access its parameters in a seamless kind of way.
Okay, yep. Yeah, that's true. But there's, let's see, so let's say you didn't use like stack frames. So you just like would store like the linkage is what it's called, like the parameters and the variables in a fixed size thing. What wouldn't you be able to do with that?
How would you basically all the functions would have to access their parameters in terms of a single pivot point, right? Instead of using their own base pointers.
Yeah. Or if, for instance, like before people did things this way, one of the things they did is each function would have its own dedicated storage area to store parameters and stuff. But then you couldn't do recursive functions. So now, basically, when the people started using stack frames and compilers started, you could have a function that called itself as many times as it wanted to, because every time it called itself, it would push a new frame onto the stack, so that it would have a brand new copy of its local storage, and so on. And so the way this kind of works is it's kind of like your memory of how you got into this classroom. So if you guys remember how you came in from the street, you walked in the front door of the building, you went to the elevator, you went up the elevator, you went into the room. So now you have, if you want to figure out how to get out of here, all you do is you just, play your memory backwards. You say, all right, the last thing I did was enter the classroom. So the first thing I'm going to do to get out is I'm going to leave the classroom and go to the elevator and go down and so on. So what we're going to do with the stack buffer overflow is we're going to overwrite the computer's memory of how it got to where it is and trick it. So if I did this to you and I said, all right, now it's time to leave the classroom, but the way you got here is you walked through the window. So you're going to be like, oh, time to leave. Walk out the window, boom, crash. That's essentially what we're going to be doing here. But I wouldn't do that because it wouldn't really do anything for me. Because if you all died, no one would do the homework. Actually, then I wouldn't have to grade any. Okay, well, but that's basically what we're going to do. If you look at how to do this on Windows, we're going to use a debugger called WinDebug, which is just a simple debugger that Microsoft makes that is actually pretty decent at machine level debugging. So we have the view of the registers and raw memory and so on. And if we've triggered a stack buffer overflow, we might see a screen like this. And I don't have a pointer, so that kind of sucks. But the important thing to look at is the status screen right here, where basically it'll show you it'll crash, so it give you an access violation, and tells you the first exception, blah blah blah, gives you the value of the registers, and then usually right here it'll tell you the instruction that it faulted at. It says, hey, I got a crash at this instruction, and it'll try and print out the instruction, but that's not what it's doing here. So did someone tell me what is actually happening here? So what is this 414141? Sorry?
The data that override the EIP.
Exactly. It's data that overwrote EIP. And how did we overwrite EIP? Or how did it get into EIP? Just to take,
Writing return address.
yes, we overwrote the return address, and then the CPU executed the return instruction, which takes from the stack the return address, loads it into EIP, and then says, all right, now try and execute what's in EIP. And that's basically what we have right here. We're trying to execute an invalid memory address. And does anyone know what the hex 414141 is? Like, what is that in ASCII? It's A's. And can anyone tell me why we do capital A's to find buffer overflows?
It's kind of ironic.
Actually, maybe at this point it is ironic.
Yeah.
I think it's actually just because someone did that a long time ago, and everyone just kept copying him. So.
No, wait, I didn't mean ironic. I meant kind of like fitting because like a bunch of A's is kind of like a stream.
Oh, yeah. I think that's kind of rationalization of why we do it. I think it really was because someone wrote a text file a long time ago, or someone taught someone how to do it, and they just like, oh, we're going to use capital A's for, some reason, and then everyone just kept copying someone else and someone else and someone else. But there's a couple things that actually make it useful. But the funny thing is, it's an unaligned memory address. So on computer architectures that care, like anything but Intel, like RISC architectures, if you try and access an unaligned memory address, it'll crash immediately. And the other thing is, usually on most systems, 414141 is not a mapped memory address. So it's not a common address that's going to actually be somewhere else. So for instance, if we used something on Windows, if we use all sevens here, like 77777, that one actually wouldn't work as well, because it's pretty likely that a library will be loaded at that memory address, and so weird other things would happen, and we'd have to kind of rewind a little bit. But by using 40141, which doesn't exist, it'll crash immediately. Yeah.
What did you mean when you said that address was unaligned?
So on like RISC architectures, Sparks, ARM chips. Actually, I can't remember if ARM needs memory to be aligned or not aligned. Well, ARM is a RISC, PowerPC, a lot of these other systems, they are much more formal than x86. So all instructions are 4 bytes wide. And they say, if you're reading 4 bytes of memory, you need to begin at an address that's divisible by 4. That's what I mean by aligned. So with Intel, you can do whatever you want. But that's kind of a special case. Most other architectures, you actually have these rules you need to abide by. Otherwise, they'll crash, because even if the memory address is mapped, like the operating system knows it's there, if you access it, if you say, I want to read 4 bytes starting at offset 1, it'll crash. Yeah.
I got a quick question. It might be a little bit tangential, but if we grab a binary and we disassemble it, is there a one-to-one correspondence between every line of assembly and every machine language instruction, or does some magic happen when we compile that assembly?
You mean when you run the binary?
No, like if we just have a program in assembly, right? Like every single line kind of becomes codified into a line of machine code.
Right.
Right. Like whether it's R-type or the other types of instructions. But what I'm saying is that is there any new lines of machine code that are introduced when we compile an assembly?
Yes. Usually there are. So for instance, like if you wrote just the smallest assembly file, like just did nothing, just did a NOP, a no-op instruction, and then you compiled it and linked it and made an executable out of it, the executable will be much larger.
Okay.
And there's actually going to be a little bit of code inserted into the binary that basically starts before it runs the function, before it runs the code that you gave it, just to kind of set things up, like set up arguments, environment variables, and so on. So there'll be extra stuff behind the scenes. So the best way to see what actually is there is to disassemble the binary, because it usually won't change your assembly code. It can, but it usually won't. But it'll add other things.
Usually the region that I wrote personally will be there more or less.
It'll be somewhere there intact.
Okay.
Yeah. All right. So yeah, basically, the classic stack buffer overflow technique is you have these stack variables, and you're feeding the application a string, and it's doing an unbounded copy with that string. And what it's going to do is it's going to copy the data into the string and overwrite stuff, including the frame pointer and return address. And the classic, easy local privilege escalation on Unix thing that you'll do is you'll put an address here for the return address, pointing into the stack again. And so when the function returns, it'll just start executing data from the stack as if they were instructions. And that's where we put our payload, blah, 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 blah. So let's actually take a look at, what this looks like. Oh, I hate this. You know what they said about never putting your passwords on a sticky note? It's all a lie. Oh, I can't paste it. All right, let's see. I know. Oh yeah, yeah. Yes, restart. This is the fast way to log into this VM because it automatically logs in and it reboots faster than I can type that password in. That gives me a coffee break. See? All right. So I'm going to start. So there's a couple. You'll need to remember this for your homework. Hey, come back. All right. So the binaries for your homework are in the difficult to remember directory here. Windows System 32 Trail of Bits. Why Trail of Bits? Because that's my company's name. All right. So here we have a few binaries. There's demo.exe, which is what I'm going to be using in the class today. So if you want to kind of do the same thing that I'm doing, just at home, make sure there's no differences, you want to run demo.exe. And then here's something very important. If you copy demo.exe to somewhere else, it'll be different, and the homework it'll be much more difficult to exploit. Because this is a modern version of Windows that has what's called dep turned on, but I made an exemption for the binary called demo.exe in this directory. So as long as you run it from here or copy another binary onto it and run it from here, it'll be easy to attack. If you copy it to your desktop, it'll be really tricky. If you get it to work, once it's copied to the desktop, you'll get extra credit. But if you don't, it'll be a lot of pain because I didn't tell you how to do it. So we're going to run demo.exe. And what this is it's just a small server, very similar to the homework binary that just listens on a network port and does stuff. And it has a very simple buffer overflow in it that we will see. So I'm going to attach a debugger to it. So we'll just leave that running. And then I need to make sure I remember the IP address here. Don't give the answer right so quickly. All right. It's a little difficult to read. That's tricky. And it looks a little easier to read. All right, we'll do that. Okay, so oops. I already did that. All right. All right. So actually, I'll show you the source code to this real quick. So, all right. Can anyone tell me where the vulnerability is in this screen full of source code? Where is the buffer overflow vulnerability? Go ahead.
We can write whatever the hell we want to buff, and there's no balance checking.
Okay. So how does the data get into buff?
One of the arguments is a pointer to a user input string.
Okay. Yep.
Username, and then in sprintf, that's like isn't it supposed to stand for safe printf?
No. I think that's like SS printf. This is string printf. It printfs into a string.
Prints it into a buffer instead of just printing it out to standard out.
Right.
So then we're copying our username string into we're copying the formatted string into buffer using user input string of arbitrary size.
Exactly. And the buff is 64 bytes. So if username is longer than 64 bytes, bad stuff happens. All right, very good. So let's actually send more than 64 bytes and see what happens. So I'm going to do a, the Perl dash E print. Actually, I'm gonna go nuts here. We're gonna print X, and I'm gonna use netcat 72.128. Is that the right IP address? I cannot remember. Oh, 72.16. Site today. Yeah, okay. All right, so does everyone know what netcat does? All right, so yeah. For those who don't, netcat is a small Unix utility that will just take data on standard in and send it over the network. So what we're going to do is we're going to print out a bunch of data. We're just going to send it straight over the network. But actually, wait, I need to do this first. Let's telnet to this server and see what it's supposed to look like. So if I, telnet to it, we connect over the network. It says, "Welcome to Snow. What is your username?" Dino. "Hello, Dino." Closes the connection. Not all that interesting. So now let's. Now let's actually send a bunch of input there. So instead of just logging in as Dino, I'm going to log in as 64 X characters. And actually, instead of 64, let's do 65 and see what happens. All right, I want to take a bet. How many people think it's going to crash? Raise your hand. Only one. Two. How many people think it's not going to crash? All right, 2, 3, 4. Oh, wait, I think the not going to crash is. All right, let's see what happens. All right, so we sent that stuff to it, and we did actually crash. But we crashed in some way that is a little difficult to kind of understand. Because what's happening is we're reading data from the EBP, which is the frame pointer, and we're getting an invalid memory address. I kind of know what's going on here, but it's pretty subtle. So we're going to kind of ignore that. But what we're going to want to do is, let's run the demo again. So one of the easy tricks when you're trying to figure out vulnerability is send different amounts of data to see how it crashes differently. And try and find the inflection points. Try and find the number of bytes that once you send more than that, something different happens until it gets to another length, and then something different happens, and something different happens, and so you can kind of see you get a better idea of what the possibilities are. So let's just blow it out of the water. We'll send double the amount of data. All right, so we send that, and now we have the crash here, where we are trying to access memory at 585858, and 58 corresponds to the capital X. That's the hexadecimal value of that ASCII byte. So we now know that data that we're specifying is getting put right into EIP. But we don't really know if this is exploitable, because we are incapable of thinking for ourselves, and we haven't been paying attention so far in the lecture. So what we're going to do is we're going to ask Microsoft what they think. So we're going to load msec and run bang exploitable and ask them to tell us. And it says, oh, it's exploitable. Cool. See that? That's usually pretty good. Read access violation at instruction pointer starting at unknown symbol, blah, 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 blah. Call from unknown symbol. Access violations at the instruction pointer are exploitable if not near null. So it basically tells us what we already know. And if you are helping developers, find and fix vulnerabilities in their code, it gives you some output that you can send to them to help them fix the bug. So all you need to do is file a bug report and tell them that at unknown symbol 585858 called from unknown symbol 585858 they have a bug, and see how popular you become. So if you're helping out developers find their bugs, try and do help them out a little bit and find out where in their code the actual bug is, and not just giving them a bunch of memory addresses that they've never seen before. All right, so that is how we can tell that there's an actual stack buffer overflow vulnerability. And that is kind of the first stage of exploitation. So I'm going to give you kind of my, how many of you did color by numbers when you were younger? Where a little drawing book, it says, all right, whatever has 1 in it, color blue, whatever has 2 in it, color red. We're going to do that for exploitation. It's pretty similar, only way more difficult. And actually not really similar at all. So, but this is my kind of guidelines for how we're going to go about writing an exploit for a vulnerability. And it's kind of a 6-step process. And I'll give you a little more detail on what you should do in each stage and what the output is, what you're going to try and achieve in each stage. So the first thing we're going to do, make sure you can trigger the vulnerability. Make sure you can get it to crash and identify that's a vulnerability. We just did that. So we're kind of already on our way. Now, the next step is we need to identify what characters we can use for our attack string. And so what I refer to as the attack string is sort of the input that you can send that actually causes the crash. And it's like usually you have to figure out like the specific piece of the input that is too long or that's invalid that causes the crash, and that's what I call the attack string. And sometimes data gets filtered. So you can't use any byte that you want in that string. So for instance, a lot of times with ASCII strings, you can't use the 0 byte. And so can someone tell me why you can't use the 0 byte in your exploit? Why would this break? Are you really taking the class, or are you just hanging out?
Absolutely not. I'm just saying that.
All right, so I'm gonna ignore you. I hope you don't take it personally. Does anyone want to tell me why a null byte would be bad? Go ahead.
A lot of times you can use a null byte to indicate the end of the input, so you're reading it to reject those null bytes.
All right, that's correct. So why would that break our exploit?
Well, because you're going to end too soon.
Exactly. If you have a null byte before, like say the buffer is 64 bytes, and say we put a null byte at byte 32, the string copy is going to get terminated by that null byte after 32 bytes, and we're not going to overwrite memory. So for many strings, for many vulnerabilities, especially ones that use ASCII strings, null byte is bad. And you want to find out what these bad bytes are early, because it gets really complicated if one of these bytes is somewhere in your shellcode. So for instance, say we didn't know that null bytes were bad, and we just used a shellcode encoder from Metasploit, or we just had it a 0 byte randomly in our shellcode. What would happen is our shellcode would only be 75% in memory. The rest would just get lost. And so our exploit would crash randomly, and we'd have to spend a lot of time debugging to find out why this happened. And sometimes it can even get more annoying, where sometimes certain byte values get replaced with other byte values. So if you have like an FF byte or 2 FF bytes, those might get replaced by another value, or we might get shortened. There's all these weird things that'll happen when input is being transformed. So rather than have crazy debugging, nightmares, it's better to try and identify these bytes early on. Figure out what character set you can use for your attack string. And so you make sure that memory addresses that you use, your shellcode, all only use those safe bytes. And third stage is identifying offsets. So in this, string, we'll say for instance, like the username. In this example, the username is our attack string, and we say, all right, if our attack string is 64 bytes long, nothing happens. But if it's longer, it crashes. So we want to find out what offset into that string is the return address. So if we find out that at offset, 78. That's where the return address begins. That's good to know, so when we want to specify the return address, we know where to put it. And we know that the rest doesn't matter. And so I call those significant elements. You find out what is something that needs to be there for your exploit to work. And sometimes with different exploits, you might need to, for instance, put in other memory addresses, like a memory address that just needs to be readable for the application to not crash until you get control. Or you might need a memory address that's writable. Or you might need a value to be 0. There's because you are, overwriting data and then letting the application continue execution, you need to make sure that everything is as it expects it to be until it uses your return address. And then what you want to do for step 5 is identify the amount of usable space for your payload. Again, you don't want your payload to get chopped in half. So what I'll do, one of the things that I'll do is at early stage is I will use a kind of a fake payload, and I will basically put a bunch of NOPs. So does everyone know what a NOP is? A no operation? It's like a single byte, and on x86 it's a single byte instruction that does nothing. So we can basically, if we make our payload a bunch of NOPs, it'll just do a whole bunch of nothing. But if we do a bunch of NOPs and then something at the end, like say we did like 2,000 bytes of NOP and then an infinite loop at the end. If we executed that infinite loop, we know that we could put at least 2,000 bytes of payload safely. Because if for some reason it crashed before it got to that infinite loop, we'd know that we didn't have 2,000 bytes, and we can kind of play with it a little bit. Once we figured out we have 2,000 bytes of space, we check the size of our payload, make sure it's less than that, and we can just drop it in. And then we get a shell. So kind of go a little over this a little more in detail. So triggering the vulnerability, it can take multiple forms in general. The demo that I'm showing you is very simple. We just send a long string. But like memory corruption vulnerabilities can happen in the parsing of just about anything. So triggering the vulnerability might include a lot more steps to get to that place where you trigger the vulnerability. So there might be a vulnerability in parsing like a PDF file or parsing like a PowerPoint presentation. So what you'll need to do to trigger the vulnerability is create an entire PDF file that has just one thing wrong with it at the right place. And that can be a lot of work. It can be a huge pain. But that's all part of figuring out how to trigger the vulnerability. It can also be in media files. It can be in decoding of media file formats. It's pretty common. It could also be when it's like for in a web browser, a lot of times they're not actual parsing bugs, they're dynamic interaction bugs. So instead of having a web page with a long string in it, what it'll be is it'll be some JavaScript that executes the right sequence of operations that causes memory to get corrupted. So basically it can be tricky, but at the end of the day, what you're trying to do is trying to deterministically make the target application crash. That is what you want to get out of the triggering the vulnerability stage. So next, we're going to identify what characters we have to play with. And I kind of talked about what the attack string is and so on. And there's a number of different bytes that'll commonly mess with your input. So null bytes I mentioned. Also, in a lot of times, white space will be a problem. So space characters, tabs, new lines, carriage returns, all that stuff may terminate the parsing earlier than you want. So you need to make sure they're not in there. And so we kind of call those bad bytes or whatever. If you use Metasploit, they always call them bad bytes. Last stage is, or not last stage, the next one is identifying the offsets. So actually, I'm going to do this differently this year. We're going to go crazy. I'm going to, okay, so we'll identify usable characters. We'll say we've already done that because we've tried, actually, I'll do that. I'll demo that right now. So I'm going to do these kind of step by step. I'm going to tell you the stage, and then I'm going to do it on the demo binary and show it to you. So let's relaunch our targets. Get that out of the way. All right. So now the binary is running, again in the debugger. All right, so now, like if I were to print A times 32 plus null plus B, oh, things are getting crazy. All right, so let's say I sent input like this, 32 A's. Can we kind of see what's going on here? I'm saying print 32 A's, and then a null byte, and then 200 B's. So this is longer than the input string, so it should crash. But I'm going to send it with the the null byte in the middle, and show you that it does not in fact crash. All right, so we send it, and we see that the binary is still running. The debugger hasn't tripped up. And also, when the binary echoes back our username to us, it only gives us the A's because it was A's between the null byte and the B's. And so one of the things that I'll do a lot, just to kind of see where various things are in my string, is I'll fill some segment with A's, another one with B's, another one with C's. And so when I see a memory address, when I see what the value is, I'll know what piece of my string it came from. And that's part of the next step, which is identifying offsets. And kind of the better way to do that is using Metasploit's pattern strings. So a pattern string is a algorithmically created string that makes it really easy to find the offset from anywhere in it. So if you see the pattern string, it's like capital A, lowercase a, 0A, and then A1, A2, blah, 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 blah. What this means is that when we get any of these 4 bytes in a memory address or in a register, we can, algorithmically find out the offset into that string where it came from. And so the two tools to do that are pattern create and pattern offset. So for instance, we use pattern create to create a string. We give it a length. So we'll say pattern create, give me a string of length, I don't know, 200 bytes. Because we know that'll be a lot larger than our input string needs to be to crash things. And then we get it to crash. And then we basically we'll grab one of these memory addresses, like we'll see, these values from a register, and say EIP has this value. And we see that in the debugger. We pass that to pattern offset, and it tells us, hey, this value is found at offset 18 in the pattern string. And so this is how we're going to find the offset of the instruction pointer, of where the return address is. So let's do that right now. And do I have this installed? No, I don't. All right. Wait a second. All right. Good. All right. So I have I have a small script here that's it's Ruby. We're using Ruby just because it's simple, and also it's what Metasploit is written in. How many of you have not ever written Ruby code in your life? Raise your hand. Almost everyone. Okay, so we'll start at the top. There's a hashbang. Does everyone know what a hashbang does on Unix? So it basically tells it, this is a Ruby file, use Ruby to do this. All right, this next line, not too tricky. Can someone tell me what this next line does? Well, it's assigning this literal string to the variable called pattern. See, this is pretty advanced Ruby here, so I hope we all can follow here. All right, and puts is put string, so it's going to print it out. Pattern plus the string, \r \n. So it's going to print the string with the new line. So it's not too tricky. And if we run it, it'll just print out the string. So now let's run this against our. All right, I want to send it to. All right, so we're going to run that against our server, and if we go to our debugger, we can see that it is crashed, which is good, and we can see that the memory address that it's trying to execute is also from the ASCII range. So all the ASCII bytes are generally in, I think from hex 30 to hex 80, hex 7F. So basically, when you see a bunch of those numbers, that's usually pretty good. So we're like, all right, excellent. That is from our pattern string. Now let's see if Metasploit has unpacked, and we can get, yes. All right, so there's pattern offset. Okay, so we give it pattern offset. We just need to give it this item to search for. So we'll give it the memory address, which is 41336 341. So what it'll tell us is that this is at byte offset 69. So what that means is that if we go back, all right, so actually, well, let's just remember that for now. Let's go back to our slideshow. All right, so the next stage is filling in our memory addresses. So we've identified sort of the memory offsets of where things, where various registers are. And if we look back at our let's look at our registers. We can see that EBP has a value from our string, and EIP also has a value from our pattern string. And so basically what I'd start with is for every register that has a value from the pattern string, pass it to pattern offset, find out where the offset is. Can anyone tell me why I don't need to pass, since I know the offset of EIP, why I don't also need to pass EBP to, or someone tell me what the offset of EBP is in my string if the offset to EIP is 69. 65. Because it's going to be right before the return address. The save frame pointer is right before the return address. So that makes it a little easier. So in filling in the memory addresses, what we'll need to do is for everything that we have identified the offset to, we'll want to specify a value for it that allows execution to continue towards running our shellcode or running data that we control. So let's do that now. So if we go back to actually let's copy this to exploit.rb. All right, so here's our exploit so far. It's just a big pattern. But what we're going to do is we're going to say our attack string I'm going to call boom. So we're going to start by just saying it's the pattern string. Oh, wait, I'm going to say pattern plus rn. Our attack string. Print attack string. All right, so now what we can do is we can actually fill in various values in the attack string. And so the reason we calculate these offsets is because it lets us say, all right, I don't care about the rest, but the bytes at a certain place I do care about. So boom, 69, I think, if I can't remember the syntax, I think I need to do that. I can specify a different value. So if I specify 4 x's, let's say set EIP to xxxx. I want to make sure that I can figure out where in my attack string the value of EIP is. And let's see, is that going to do it? Yeah, okay, that's the right syntax. So if we look at my attack string now, like I just printed it out, there's xxxx right there. So let's restart the server and see if if we successfully set EIP to xxxxx. All right, exploits. 28. Boom. Fire in the hole. All right. And we can see that EIP is xxxxx. So we've chosen the right place for EIP. That's good. But now the question is, well, we don't really want EIP to be xxxxx. We want it to be something that executes a payload. So we need to kind of figure out something better. So that is the next stage. Oh wait, actually that's the second part of this stage is if we've overwritten a return address, we want to find a useful memory address that's going to help us get control. So there's a couple things we can do here. The first thing we can do is we can just guess a stack address and see what that does. That might work. So if we look at the value of ESP, we could say, all right, I will overwrite EIP with 0023AED0. Can someone tell me why that won't work? It's got zeros in it. It's got the null byte. So remember, in a memory address, it's not 1 0, it's 2 zeros. So, the 2 zeros means it's a null byte. So if, for instance, like this address right here, the 01CC9288, that's not a problem because 1 0 is not an issue, but the 2 zeros, meaning the byte value 0, that's when we're hosed. So we can't specify the stack address directly. We could specify another one of these addresses, like if we look at ESI, we could say, all right, we could specify that memory address, but let's see what's there. So if we go to our memory view, and type in ESI to show us the memory at ESI, it will just sit there. All right, we'll do all with command line. So in WinDebug, dd is display dwords. So when I type dd space and then a register, it'll show me the memory at that register. Or if I type dd and a memory address, it'll try and read it out. But if I look at ESI, that's all memory that doesn't exist. But if I look at the memory at ESP, what's useful, so this shows me, yes, there's memory there, and it all has this value. So can anyone tell me what this is? Sorry? It's the pattern string. So that means that ESP points to my data, which makes sense because we're overflowing data on the stack. So if I could get the CPU to just execute memory starting at the memory address pointed to by ESP, we'll be executing our data, and we'll be getting on our way to the shell. So what I want to do is I want to get it to do that. So does anyone have an idea of how I can easily tell the process to execute data from ESP? Yeah.
Can you encode that null byte?
Sorry?
Can you encode that memory location so that we don't have any null bytes in the string?
That's a good idea. Sometimes you can do that. Sometimes you can encode the data so that the null byte gets kind of replaced with null, like when it's getting interpreted, so you can kind of be tricky that way. In this case, we can't do it. So we don't have any like tricks where we can get data to get decoded for us. So we'll have to do something else. All right, I'm not letting you say the answer either. You've done this before. That's cheating. I gotta make them squirm. All right. So what I wanted to do, if I could somehow get the process to execute, like let's just think of an instruction that I want the process to execute, like jump ESP. So say I could get the process to execute jump ESP. What that would do is it would immediately start executing data from ESP. Yeah.
Oh, can we jump to the loaded library that has to jump ESP?
Exactly. You're so close. So if I can find a jump ESP in a loaded library and I can specify that address for the return address, it'll be just like it executed it, and it will do it and then start executing data from ESP. So, but there's a problem here. The instruction jump ESP is kind of weird. Like, can you think of a reason why a compiler would generate code so that the process would just jump to its stack pointer, like, or do a call ESP, like it would call a function written on the stack? Is there a reason that a program would do this? I'm not answering that. I'm not letting you answer either. Does anyone go? Sorry? No, not recursion. But the answer is there is no reason that this would ever happen. There is virtually no reason why a compiler would generate code, would put the instruction jump ESP into a binary. But it doesn't matter. Because of the way that Intel instructions work is they're unaligned. So we can, if we find the exact instruction, the exact byte sequence that decodes to jump ESP anywhere in executable memory, it's just as if the instruction existed there. So the way Intel instructions are, they're variable length. So they're between 1 and 14 bytes long. So say you have a 14-byte crazy long instruction. And if you start executing bytes from the middle of it, the CPU will interpret it as a different instruction. On other architectures, you can't do this. On real architectures, as I call them, you have to execute instructions at aligned memory addresses so that you can't jump midstream. But on x86, you can. And what's very helpful is that the instruction jump ESP is a very short instruction encoding. So if I say instruction encoding, are people kind of understanding what this is? Like when I write assembly code, I write in mnemonics. I say JMP space ESP. But when I run the assembler, it turns it into machine code, which is binary. So it'll turn it to FFE4, if I recall. And that is machine code. That is the instruction encoding. And say you don't actually remember all these offhand. What we can do is we can use WinDebug to kind of remind us what the instruction encoding is for something using the A command, which is assemble. So what the A command does, well, we'll give it a memory address. We'll just say A ESP. So that says read assembly code for, in the command line, and then assemble it and write the encoded bytes to that memory address. So we'll say AESP, and then the prompt changes, and it starts asking for instructions. So I'm going to just say nop, just as an example, and then I'm going to say jump ESP, ignore those, nop, and then when I'm done, I hit enter again. So now, if I type DDESP, the bytes have changed. But actually, I want to do DBESP. I want to see it by byte. So DB is dump bytes, not D words, and it prints it out byte by byte. And so also, if I use the U command, which stands for unassemble, which for some reason, because you can't use disassemble because D is already taken for dump. But if I say unassemble beginning at ESP, it'll disassemble the bytes there and tell me what they are. So you can see that it has the memory address, it has the encoding of the instruction, and then the mnemonic for the instruction right there. So NOPs are hex byte 90, jump ESP is FFE4. I only remember that because I was reviewing this stuff an hour ago. I'm not actually that cool to remember all these instruction encodings off the top of my head. But what that means is if I can find FFE4 anywhere in memory, in an executable memory page, and I can specify that address for the return address, it'll execute that instruction. So let's actually see if we can find that. So to find it, we're going to use this WinDebug command, the S command. So let's see, it's S. I make it. The WinDebug commands are all very easy to remember. Yeah, I didn't write this to myself. I think it's, oh yeah, it's then the beginning memory address, 1, 2, 3, 4, 5, 6, 7, 8, and then how it's the size of the window, 1, 2, 3, 4, 5, 6, 7, 8. So basically, this tells us to search beginning at address 0, and then you tell it kind of the size to search, and I'm giving it 8 Fs. So I'm saying search the entire address space, and then I can give it a list of bytes as the pattern to search for. So FFE4. So I'm going to say search all of memory for FFE4s. And it's going to find some of them, and just boom, it finds a ton of them. Yeah, that's a lot of them. So you can see that all these places, like so these memory addresses right here, that have the byte sequence FFE4. But one of the things we need to make sure is that these are read-only memory pages, because we don't want these to be coincidentally there by data that can get changed. We want to make sure that these are actually in other code segments of a loaded library. So for instance, so the one way we can check that is we can use this very obscure command, vprot, to show us the memory protections of a memory address. So like I'll just choose one of these here. And if I use vprot, it'll tell me that it's read-only, which usually means that it's code. There's another command called bang address, but it's broken on the VM because the symbols are bad, so I can't actually use it. But if I look at the module list, 7E49 will probably be a loaded library. So if I look at 7E41, yeah, so 7E41 to 7E4A, 7E49 is in that range, is user 32. So that's a loaded library, loaded DLL, and this memory address right here is in there. And if I type U and that memory address, like say, just to remind ourselves, so disassemble starting there, and show me what the instructions are. You can see it's jump ESP and then gibberish. Well, we don't care that gibberish follows it, because after we've jumped into the stack pointer, we're never going to return here, so we don't, just having that one instruction is all we need. So here's another thing. You guys notice that when I searched for FFE4, there's a gazillion of them. So statistically, it should be very rare that the two people's homework exploits will use the same memory address. If two homeworks use the same memory address, I should go try and win the lottery. So there should be almost no way that in this entire list of 10,000 possible choices, two people choose the same one. So just a hint there. All right, so let's actually put this memory address into our exploit and see what happens. So 7E49227. Uh, 7E49227. Right, 227C. All right. Oh yeah, one other thing I should probably cover. DB ESP. All right. So when I looked at ESP, when I did DD and dumped it by D words by 32-bit values, and when I dumped it by 8-bit bytes, you notice that the bytes are in a different order, right? You see that that's 9090FFE4, but here it's E4FF9090. Can someone tell me why that's the case? Someone that hasn't been in this class for 5 years? How many years have you? 4 years. Okay. Julian's been going to this class since he was in high school. All right. Yes. Correct. Yeah. The Intel processor is little endian, which means that it stores the little end of the memory first. For extra bonus points, can anyone tell me why processors are called little endian or big endian, or what that's a reference to? I'll give you a hint. It's a literature reference. Gulliver's Travels by Jonathan Swift. Yeah. Yeah. So that's just also why Intel is just weird. But what it means is that if we put in, say, like we just typed in the memory string here, like X7E4922X7C. When we write it like a string like that, it writes it in big endian order, and so that would actually not be the correct memory address once it read it out. So let's actually run that just to kind of prove to you that I'm not lying, because most of the time I'm lying. Also because this is a common error that you're going to hit in your homework, and it's good to find it now. All right, so we run our exploit, and you can see that our memory address is wrong. It's all kind of, reversed. So what we want to do is we want to reverse it in our string here. So we 7C 22 49 7E. All right, so now let's try that. Also, something I forgot to mention. When I'm attaching the debugger, is everyone kind of following? I run the binary here, and then I go to WinDebug, I type F6, or kind of the menu, I can say attach to a process, and then I find demo.exe. It's the last process I launched, so it's always going to be at the bottom. Hit OK, and then the debugger stops. I mean, this doesn't mean it crashed yet, because when you attach the debugger, it's going to just hang there and say, hey, what do you want to do? And we're going to tell it, we want to tell it to continue running the application, so we can say go, or I have probably gone through the sequence of attaching and continuing a debugger like 1,000,000 times in my life. So at this point, it's just F6G. So we're now running. You see it says debuggy is running. That's where we want to be. Yeah.
Question, also slightly unrelated.
Yeah.
How is it that the debugger can just inject a breakpoint, just like can inject that CC straight onto another process's memory?
So on Windows and Linux, most operating systems, if two processes are running as the same user, you can debug the other process. So that the operating system lets you do that. And so if you can debug the process, what that means, you can read and write its memory completely arbitrarily. So what the debugger can do is it can say, just change this memory to a CC, and then it will hit a breakpoint. And that's the way debugging actually works. Is like when you say set a breakpoint at this memory address, what the debugger does is it changes the instructions at that address to the CC byte, which is the debug interrupt, and then says, okay, continue running. And so then once it tries to execute that instruction, it gets the breakpoint, or it gets the debugger steps in, and then it removes the breakpoint and puts the instruction back. And that's just how operating systems mostly work. But on some systems, like Mac OS X and the iPhone, you can't actually debug other processes. by just being the same user. So you know, if the two running as the same user, you can't just attach to it and read and write its memory. You have to have extra privileges to be able to do that. But on Windows and Linux and all those things, you can just debug. Except for on Vista, there's like they have like protected processes for DRM stuff that you can't debug even though they're running as you, but that's all this extra stuff. All right, so now let's see what happens when we send the correct memory address. So boom, send that. All right, so we did that, and it crashes at this address here, and it has this crazy address, or this crazy instruction, ARPL. Can anyone tell me what the ARPL instruction does? Because I actually don't know. Does anyone have an idea of what's going on here? Like, what's happening right now? Did I see a hand moving back there?
Jump ESP.
You did a jump ESP.
Yeah, now that's what's on stack.
Exactly. So if you look at ESP, it's the same value as right there. And if I use the U command for unassemble, I see right here at ESP is ARPL word pointer blah 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 blah, which is not all that useful. But what this means is that we're now executing instructions from our pattern string. So if we replace that pattern string with bytes like that we want to execute, we're almost there. So now let's figure out what offset we've jumped to. So if I type dd, actually, so it's this memory address. Oh, it's ESP. So if I type dd ESP, I get this value right here, and so I'm going to pass that to pattern offset to find out where that is. So 6341. Pattern offset 6341 3463 3463. These are Metasploit scripts. So if you actually, what we're probably going to do is we're probably going to just install Metasploit into the Windows VM. I'll send an email out later today with later tonight with kind of what to do, and you can use it there. What I usually do is I run the VM and I attack from outside the VM, just so it's more realistic that I'm attacking across the network. Because if you're attacking on the same host, sometimes you might take shortcuts that you can't actually use. Like you'll look at a memory address on your local system, but it'll be the same system, and it kind of messes you up. So I always do it across the network just to be a little more pedantic. So if I run pattern offset, it tells me that at offset 73, that's where I started executing. So let's look back at my exploit script. So if I look at 73, I think I can do this, equals, all right, make these capital, it doesn't really matter. All right, so this is actually, I'm going to call this payload equals that, and then at offset 73, we'll write our payload. So yeah, that did it. So all right. So can anyone tell me what my payload is going to do here if I get those bytes to execute? I think you know.
It's a debugger. It's like a break.
It's a breakpoint. Basically, it's a it's a special interrupt that indicates a breakpoint. So one of the nice things about this is I know that if I hit that, if I execute those bytes, it'll say breakpoint, and I look at the memory address, and I'm like, cool, I'm executing my own code. Yeah.
Is there any way, since that's like a debug, like a universal debug operation, like is there any way that we can further encode a string to print out? Does that even exist?
There might be. I don't think so though, because the way that Windows does like debug output is there's actually a function called print debug string or output debug string. But what we can do, just to kind of help us, is we'll just put like we'll say our payload is cc I am awesome. So So say we try and execute this string. If we execute the interrupt and we look at the memory and it says I am awesome, we know that we are in fact awesome. If it says something else, we know that our whole life is a lie. So let's hope that our whole lives are not lies. So let's see. All right, we're running. Let me run our exploits. Okay, so we got the breakpoint. So now we can run db to dump the bytes at, actually we'll do it at EIP. We'll say from where we're executing now, dump bytes, EIP. Oh, good. It says I am awesome, because otherwise I had to go home. So we're good. So that's one trick. So you can make sure that it's your that's your bytes. So now let's do something. Actually, now we go back to our color by numbers. So we filled in the memory addresses. The main memory address we wanted to fill in was EIP, and we filled in the address that would actually get it to execute from the stack. So we're pretty good. So our next step is to figure out how much usable space we have for the payload. And so what I do is I space it out by putting a bunch of nops followed by a debug interrupt. So then we know that if we executed all the nops and hit that interrupt, we have at least that much space, and we can keep increasing the amount of space until we get bored or until we know that we have enough for our payload. And most exploit payloads, at least in Metasploit, they have an initial stage that's a few hundred bytes. So if we have 2,000 bytes for payload, that's usually pretty good. If we have 4,000, we have enough space to do whatever we want. If we only have 20 bytes, we're kind of hosed. But what we're going to do is we're going to make sure that we have enough space for the payload now. So let's start our server again. Attach. All right, so we edit our exploit. So now our payload is still going to be the hex byte I am awesome, but we're going to put some nops before it. So our nops is going to be 0x90 times some size. So we'll start with 100. So instead of just putting our payload right there, we're going to put nop plus payload. So that, nops. So it's going to print 100 nops and then our payload. And so then we'll know that our payload is at least, our payload space, if this works, will be at least 100 bytes. So we can see that we got, when we just print it out to standard out and look at it, we got a bunch of binary garbage, and then I'm awesome. So, it's printing out the right thing. So let's do that. We go back to the debugger. We see that we hit our breakpoint. We do db EIP. We are still awesome. Good. So 100 bytes isn't all that much. Let's raise the stakes here. All right. How big should I try this time? First number that gets called out wins.
4 billion.
Oh, come on.
2,000.
2,000. All right. Can someone tell me why 4 billion is a bad idea? Yeah, in the 32-bit OS, it'll be almost larger than the entire address space. But that'll actually, I'll come back to that because that's a good thing, a useful thing to show. So let's do 2,000 and see if that works. All right, 2,000 works. That's good. So now let's try a suggestion from the peanut gallery and back, and quickly learn why listening to what they say is a bad idea. I'm not going to do 2 billion, but I'm going to do something like, I'll do 200,000. So let's say I created a string that's way too large. Let's see what happens here. All right, so we're running. On that. Okay. Actually, that is not what I expected. I think I need more. Because that is, yeah, wait, actually, that is not what I expected. What I'm hoping. All right, 2 megabytes of NOP. Oh wait, actually, it's not that many. So let's do. That should probably be. Actually, probably good enough. Nope, that's still not enough. All right, I'm gonna try one more time, and if that doesn't work, I'll give up. Times. We're going to send 100 megabytes of NOPs. It's probably enough. No, wait. We're crashing for a different reason. All right, so when I was hoping that would happen, but not happening, not cooperating. A lot of times with like string copies, if you send way too much data, what's going to happen is you're going to run off the top of the stack, and you'll basically get an access violation where you're trying to write data to an unmapped memory page, and so it'll look like a completely different crash. And I was hoping to be able to show that to you so that you would kind of know what it looks like, but we are. Oh. Yeah, I'm completely retarded. The problem is I'm still overriding EIP correctly, so let's not do that. There we go. So if we don't have, EIP at the right place, but say we're just sending way too long of a string, then the right thing will happen. This is what happens when you improvise. Go. All right. No. All right. Screw that. All right. But basically, we found out that 2,000 bytes of no ops are enough. That we actually, we can fit and we execute our full payload because it executes all the NOPs and then our breakpoint. So that is what lets us go to the next stage. So the next stage is to drop in the payload. So what's common these days is to get your you'll have what's called payload encoders, and we'll learn about these more in when we talk about Metasploit later. So we don't really need to care about them too much because for the homework this week, I'm going to give you a payload that works. Like we have one on the web that you just download, and it's in Ruby. You just drop it in the right place, and it should execute. And for simple vulnerabilities, just avoiding null will be enough, and that's, I think, the case here. So now, let's actually drop in the payload. So the file you'll download is payload. Yeah. So if you, we'll put this on the web. It's just this file here that says payload equals and a bunch of hex bytes, and we generated this with Metasploit, and what it does is, when we print it out, it tells us the kind of the parameters that the payload was configured with. So L port is 444, and in this case what that means is that that's the port that the shell is going to listen on, because the payload is called Windows/shell bind TCP. So it's for Windows, and what it's going to do is it's going to bind an interactive command.exe shell on a TCP port, and that's going to be TCP port 44444. And then exit func equals process means that once it's done, it's going to call the function exit process to exit the process. So let's copy that. So our payload is not going to be that anymore. It's going to be that. All right, so payload equals all this hex stuff, and then our attack string actually is going to be still going to have the NOPs. I'll just say, yeah, 1,000. We're going to put 1,000 NOPs before it, and one of the things that Metasploit tells us at the top is that it's a 341 byte payload. So 1,000 bytes of NOPS plus 300 bytes of payload still fits in the 2,000 bytes that we've sized up. So this will still work. And the reason we want the NOPS there is because depending on how the payload was configured, it may or may not adjust the stack pointer. So because we're executing directly, because we've jumped to ESP, we're executing from where ESP points to. So if the payload tries to do stuff to the stack, it's going to step all over itself. It'll start pushing stuff onto the stack, which will be its own code. So if we put a bunch of NOPS before it, we make sure that ESP points to the top of all those NOPS, and then the code is farther away from that. So when the code starts pushing stuff on the stack, it's not overwriting itself. So one way around this is you can tell Metasploit to insert an instruction to adjust the stack pointer before it starts using the stack, but I can't remember if we did that or not. So just be on the safe side, I'm going to make sure that there's 1,000 bytes of NOPS before we execute the payload. So let's test the debugger. And now let's run our exploit. Okay, exploit is run. And we go to the debugger. So can someone tell me what's different now than the other 20 times that I've switched the screen to the debugger? Correct. Got an unknown exception, but it didn't crash. So that's good. So now let's launch another command prompt and type netstat-an findster listen. So if we look at netstat, which dumps out all the network connections, and we looked for only ones that are listening, we see there's now a listening socket on port 44444. So now let's go back to our attacker machine and type nc 122.116.1.128 port 4444. So let's connect to it and see what's listening on it. Oh, look at that. There's a shell. So we can type commands, and we now have remote access to the system, assuming they're running this demo executable that is vulnerable as all hell. So, do this if you're running this, when you're doing your homework, do it behind a firewall, and I'd recommend not doing it. Well, actually, it's really fun if you all do it on the same wireless network. And whoever gets the exploit first gets to own all their friends. So it makes you work really fast. But now if we do stuff, we have full access. We have access to the system with the same privileges as the user who started the executable that we attacked. So we can read files. We can go into documents and settings. Click Attic Vic, desktop, and we can echo "You are owned" into "Hey loser.txt." So if we go back to, if we're just sitting here working on our computer, we see a new text file has appeared here called "Hey loser." We're like, wait, I'm not a loser, but I guess I am owned. So you can see that, with this shell, I can do whatever I want to the system of, of who's running here. So that is basically what we want to do. And then once we exit, it's not crashing. It's actually executing, but the debugger is just letting us know that, the process is going away in case we want to do anything before it shuts down. So like we can see what this looks like kind of faster. Like if we we do it not with the debugger attached, where we just run demo.exe, we run our exploit, we connect to the shell, yay, that works. We exit, and then we just see that the process has exited. But there hasn't been an alert or a pop-up or anything on the desktop. So this poor what do I call his name? Click Addict Vic. This poor Vic, he's sitting here like playing solitaire. Wait, what is it? Solitaire? I can't remember the name of solitaire on the name of the XE, but
MSP.
oh, MSP, yeah. He's drawing. This is all he does at work all day. He is totally worthless. But you're attacking his corporate workstation, and he doesn't see anything happen. So while he's drawing, you are going through his files and looking at all his horrible, horrible pictures.
What matters is that Min expect to find if he was looking at like error logs or something in the back. I mean, we're still
That's-
crashing the program, right?
Right. That is a good question. So actually, I need to go to administrator. See. All right. So let's say we looked at the event viewer as an administrator, and let's see if anything happened there. So nothing in the system log. Oh, we'll check the security log. See if anything. I mean, nothing really out of the ordinary here. Actually, if we go to the application log, we still don't see anything. So if we cause some crashes, those will often appear in the application log. So like if I had a debugger always attached, but let's run this thing. I have too many shells. And let's make it crash without the debugger attached and see what happens. So to make it crash, we're going to just not put in a return address and run it. So it crashed it, and did we actually get anything? Nope. In this case, we didn't get anything. So.
I think you might need to refresh the window because it's Windows.
Because it's what?
You might need to refresh it.
Oh, yeah. Let's. Nope. Nope. It crashed, and we still didn't get any notification. So sometimes that'll happen. I think in this case it's because I compiled it with with MinGW. But depending on the process, it may generate a log, it may not. One thing that you will definitely see if you're lucky and unlucky at the exact same time. We run the exploit, we connect, we're doing stuff. If you just happen to be on the server and type netstat and just see what's we will see this connection here, a network connection to port 444, and actually let's exit that. All right, so and then if I looked at actually I don't want to look at Task Manager, I want to look at Process Explorer. So if we look at Process Explorer, we can see here's a command.exe that launched demo.exe, and that's normal, that's what we did. But demo.exe launched command.exe. That is very strange, because demo.exe is not supposed to ever do that. So if, for instance, you see, iexplore.exe launched command.exe, that's very weird, right? Because when is your browser going to run a shell? Unless you went to my web page and I made it run a shell for me. So that's kind of something that you'll see. But you have to notice it going on. And I think that is, let me see if I, yeah, live demo time. So normally it goes to 8 o'clock, right? 8:30? Sorry? Wait. Julian? Well, all right, let me see how many slides I have left for this, because I think that's... That's a lot.
Get to the good part.
It's the good part. Yeah, I was gonna say, all right, so I will keep talking for the next 20 minutes to kind of get through some of this stuff, because I want to kind of end with a lot of this. So the way that I showed you how to do this exploit, and this is exactly what you guys are going to do for your homework. You're going to, I gave you a different binary that you should have found the vulnerability in already, because if you have to start there, it's going to take you extra long. But you find the vulnerability, and the vulnerability is much trickier than this one. The vulnerability where you just send a long string and it crashes. But to be fair, there are still, well, every now and then you'll find things that are like this. You send a long string and they still crash. But so the vulnerability, the homework that we're giving you is actually trickier to find the vulnerability in than things that I've really found vulnerabilities in the wild. Yeah.
So we're gonna have to disassemble our demo.exe.
Well, you have to disassemble the homework.exe, find where the vulnerability is, and then write the exploit to send the right input to trigger that and get it to crash. And then once you figured out how to get it to crash, you need to do what I just did over the last hour to get a shell. And so the homework is turning in a exploit, a small Ruby script that gives me a shell. And make sure you don't have the same return address as everyone else. If you just chose randomly from the list, you should be good. So this is how easy it is to exploit stuff on kind of old systems. Like Windows 2000 is about the last version. Actually, no, Windows XP Service Pack 1 is the last version of Windows that is that easy. As of Windows XP Service Pack 2, Microsoft started creating what are called exploitation mitigations. And they're designed to be generic defenses against exploitation of vulnerabilities. And the rationale behind this is that it's impossible to find and fix every vulnerability. So what we're going to do is we're going to build a safety net so that the vulnerabilities that do exist that people find are going to be more difficult or ideally impossible to exploit. And there's a kind of a variety of approaches here. One is having more stringent memory page protections. For instance, making sure that you can't just execute data out of the stack and saying the stack should only be readable and writable. It should not be executable. So that's one approach. Another is runtime validation. You can do stuff like, say, before we use a return address, we should make sure that it hasn't been changed underneath us. If it's been changed underneath us, we're just going to halt and not actually use it. The third approach is obfuscation and randomization. You notice that we chose a memory address that had a jump ESP in it, right? Well, what if every time we ran the server, all the executable code in memory was in a different place? So then if we found a memory address one time that was a jump ESP, the next time we ran the binary, that would not be a jump ESP. And that would make exploitation more difficult. Those are kind of the three approaches. But keep in mind that this is not perfect. These are generic approaches. They cannot, like one approach, or even all of them, will not make every vulnerability non-exploitable. It'll just make a lot of them non-exploitable, and the ones that it doesn't make non-exploitable, it'll make more difficult to exploit. So here's kind of the timeline of what happened. Up until XP Service Pack 1, basically there were no mitigations, and you could corrupt the stack return address, and you could also corrupt the metadata on the heap. When Windows Server 2003 came out, they built what are called stack cookies, and I'll talk a little bit about what those are. XP Service Pack 2 was kind of the big one. This is where they really put a lot of stuff in there. They had stack cookies, heap cookies, dep, also something called safe SEH, another mitigation, and then with Vista they had ASLR, which was kind of invented by a project for Linux called was it PAX? Yeah, it was PAX. That basically invented this, and then Windows just kind of did the same thing. Let's talk about each of what these mitigations are and what kind of attacks they stop. So stack cookies are a way of protecting the return address on the stack. And the idea is for each function that has buffers that might be vulnerable, you're going to generate a random value called the canary or the cookie, put it on the stack between the stack variables and the metadata, like the frame pointer and the saved return address. So and then before you return, you're going to check to make sure that canary has the same value that it used to. So if the canary gets overwritten, you don't use the frame pointer or the save frame pointer or the save EIP, the return address. Pretty simple idea, but it requires recompiling all of your software with a new compiler. And so, for instance, Microsoft did this in Windows Server 2003. They compiled the entire base operating system with it, but a lot of popular third-party software only started using stack canaries in the last year or two. So for any compiler, any change that requires recompilation by Microsoft, it generally takes about 5 years for it to end up in the majority of third-party software. So the way around that is there's another exploitation technique that involves overriding structured exception handling frames. And so what structured exception handling is it's a thing supported by the Windows operating systems that support exceptions at a very low level. And so for example, in C, you can use try except blocks, and if there's a crash, it goes to the except block to try and handle it. But the way it's implemented is whenever you create a try block or a try and except block, a exception handler frame is put on the stack. And so, so on the stack, at some point past the canary, a few frames up, there might be a exception handler frame. And what these SEH frames have is two values, a pointer to the next frame and a pointer to a function pointer to the exception handler, or the exception filter, that basically is a function that determines whether it should handle the exception or not. But that's a function pointer that you can overwrite. And so if you overwrite past the canary, past the return address, and a whole bunch more, kind of what I'm talking about here, you just overwrite a whole bunch more, you'll overwrite one of those SEH frames. And if you keep overwriting past that SEH frame until you run off the top of the stack, what'll happen is it'll cause an exception, and then Windows will start looking for exception handler frames to handle the exception, and it'll use your overwritten function pointer in one or more of those SEH frames. And so for a while, people were using this to gain control. So Microsoft had the stack canaries, and I'm sure a lot of people there and a lot of people everywhere else thought that stack buffer overflows on Windows are now dead. We'll have to find something else. Well, if you do this, you can still exploit stack buffer overflows in many cases. Not all of them, but still a large number of them. And so right after Microsoft came out with the stack protection in Server 2003, David Litchfield wrote a paper talking about how to defeat it, introducing this technique. So to stop that, Microsoft had another approach, and I think this was in XP Service Pack 2. This was called Safe SEH. So the idea here is if you compiled your binary with Safe SEH, it would make a table in the binary of all the exception handlers, so that if you overwrote the function pointer to an exception handler, it would know that it's different. So when an exception happens, it makes sure that that the exception handler is in one of those tables. However, basically there's a gap here. To be safe, you had to have every library in the address space compiled with Safe SEH, because if one wasn't compiled with Safe SEH, Windows would have no way of knowing what the legitimate exception handlers were in that binary. So, for instance, like we used a jump ESP to gain control. What you would do, well, that's kind of a bad example. Back in the day, you could do a jump EDI, a jump to another register to actually jump into your data. Basically, you would just look for a jump EDI in one of the modules that wasn't compiled with Safe SEH. Because if you used an address in a module that was compiled with Safe SEH, Windows would say, actually, that's not one of the registered exception handlers. We're going to halt, no go. But if you used a memory address from a binary that wasn't compiled with Safe SEH, it would allow it. So you could still get the attack. And so that meant that popular applications would have to make sure everything was compiled with Safe SEH. And so for things like, I think QuickTime, there was like one DLL that wasn't compiled with Safe SEH up until around 2007 or 2008. So 5 years after Microsoft came out with Safe SEH, they still hadn't made that program safe. Another mitigation is called safe unlinking. This is how, if you overflow a heap buffer overflow, you could hit the heap metadata and use that to write a chosen value to a chosen place. So XP Service Pack 2 had something that would check those pointers to make sure they weren't overwritten. And the idea there is also to use a cookie, right before it, so that if that cookie gets overwritten, they know not to trust the other data. Yeah.
Is it infeasible to research the cookie generation algorithm and then just kind of overwrite, craft your buffer so that we overwrite
with the right
hash or the right?
You can do that. It's not like, usually they're pretty good about that because that's pretty easy for them to make sure that it's random. But there are other things you can do. So for instance, if you have one type of vulnerability that lets you dump memory, so like for instance, say in a web browser, you were able to overflow the buffer but not completely so that it didn't terminate the string, and then you read the string back, you would actually read the canary value. Because the string buffer would fill all of the stack frame, and you'd make sure that it didn't have a null, but also would terminate there, and so there'd be a null somewhere up on the stack. So you'd get the original string back if you read it in JavaScript, with some, some binary values that were the return address or the frame pointer or canary, frame pointer, return address. And then you could say, oh, now I know what the canary is. So now when I'm going to overwrite the canary, I'm going to put that value there.
So the canary is a literal value on the stack. We're not pointing to a.
Yeah, it's a 32-bit value. But people thought of that. So what Microsoft did is they said, all right, now we're going to make the canary different every time. So we're going to do canary encryption, or I can't remember what they call it. So what they do is instead of what they did in the initial version was just generate a random value when you started the process, and then use that canary value all throughout.
So now we're making a hash of it and then comparing it internally.
Close. Now what they do is they say we take that random value and we XOR it with the frame pointer, and then store that. So that makes it different enough that it's hard to guess. So that if you read the canary from one function and then try and use it somewhere else, it's not going to work. So basically, the way all of this works is that, attackers will figure out a new attack. Microsoft will figure out a way to fix it, and then release it in an operating system 5 years later, and then attackers will move on to the next. And the benefit is it's easier for attackers to get to the next step because Microsoft has to fix a lot of these. They say, all right, we got to make a new operating system level mitigation, and we'll do that in the operating system that's released in 2 or 3 years. And then it'll protect many things. But if it requires recompilation, it requires Adobe, requires Apple, requires everyone to recompile their software, it's going to take 5 more years for all that software to get recompiled and everyone to be using it. So it's a very slow process from the defense side. But from the attack side, usually it takes a year or two from when a new mitigation is released until it's broken. So it's an interesting battle. One of the big mitigations is DEP. This was actually a pretty good mechanism because it's generic, it's harder to get around, and with DEP with ASLR actually are a pretty good combo. And I'll tell you what ASLR is in a minute. But the idea with DEP is that if a page shouldn't have code, you shouldn't execute memory from it. Pretty simple. But the way that the x86 processor was originally designed, they didn't really have a protection bit that meant executable or not. They just had memory pages were either readable, writable, or both. And the operating system would keep track of which ones it thought were executable, but the processor would still execute would execute instructions from memory that wasn't executable. So what DEP does is it adds what I call the I really mean it bit, that if you say it's not executable, the processor won't actually execute bytes from it. And we can actually check to see which processes have DEP using Process Explorer. And keep in mind, you need to run Process Explorer as administrator to be able to see the DEP column. So if you run it and you just see under DEP NA, 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 you need to run Process Explorer as administrator. And you can see here that basically all of them have DEP enabled. But this is what I did for this VM. I told the system to turn off DEP for demo and homework, so that when you do that, it'll actually it'll be easier to exploit, because bypassing DEP for your first exploit is a bit tricky. And there's a couple ways to actually bypass DEP. So what we can do is we can use what's called return to libc or code reuse, or what people now call return-oriented programming. And the idea is we know where a bunch of usable code is, we can jump there and execute that instead of executing our shell code. So for instance, there's a function called virtual protect. And what that does, that changes the protections of a memory page. So instead of returning to our shell code, we could return to the function virtual protect and tell it to make our stack executable and then return into our stack. And so the idea of using return to libc is to do that, because all these functions are at known places. They're in the standard system libraries and they don't move. So we can just borrow that code and turn off DEP. And when Microsoft first released DEP, there was even a single location in memory that would just turn off DEP for the entire process. So if you knew this one place and you said, oh, just jump there, and it just turns off DEP, and then you just execute memory from wherever you want. It was just a instant off switch. So then Microsoft fixed that, like in the next service pack, with permanent DEP, where once it's turned on, you can't turn it off. But it was only a few processes used that, and it took until Internet Explorer 8 for Internet Explorer to actually opt in to permanent dep, so you couldn't turn it off. So even in IE7 on Vista, like a pretty state-of-the-art browser as of 2006, 2007, you could still do this kind of trick. So yeah, here's, I'll send out the slides. You guys can read through this more. There's a cool trick that was published about a couple years ago, or a year and a half ago, that would basically return to the function called write process memory. And the idea here is write process memory is a function that is used by the debugger to actually write memory to a different process. But if you pass a special argument, you can use it to write to your own process. And write process memory has a nice feature where if it notices that the memory you're trying to write to is not writable, it will make it writable so you can actually write the data there. So if you return to write process memory, you can use it to write data that you want kind of to wherever you want. And this is another way you could bypass dep. And you should probably read the post to kind of fully understand it. But the latest and greatest hotness is what's called return-oriented programming. And this is a generalization of, wait, do I really not have a slide on ASLR? A generalization of kind of the return to libc stuff that's a little different and a little more powerful. And so what you need to kind of keep in mind for why this actually works the way it does is because when we overwrite the return address, we can actually replace that with an address of a function and overwrite the arguments on the stack as well. And so that's the main idea with return to libc, is that we can actually overwrite the return address and simulate a function call. These slides are totally messed up. But the idea is, yeah, we can also chain the returns so here's our stack. If we just overwrite the return address with what's labeled function, and then there's like an empty space, and then the arguments, we can put those values for the arguments there and simulate a function call. And what's more, we can actually stack these together. So we can chain a function call to function A, and then it'll return to a function call to function B, and we can kind of chain these together and get something a little more useful. And we can kind of build a payload this way. And kind of here's an example of how it works. Like say we've overwritten the stack, and you can see on the right where the values we've overwritten the stack with, and the left are the instructions that execute. Well, the return address or the return instruction will pop a value off the stack, and it's going to start executing a function. We can see that the instructions here are the typical function prolog, and it's going to save the function pointer or save the frame pointer, and then it's going to use the arguments here. It's going to pull them off the stack, which is data that we control. And then it's going to restore the frame pointer and then return to the next thing on the stack. And that'll be the address of an instruction sequence that will skip over the arguments. It'll just pop, and then ret, and it'll take the address of the next function to execute, and then do the same. The whole idea with ROP is that instead of returning to functions, we're going to return to single instructions followed by a return instruction. And because x86 instructions are unaligned, we can find these unintended sequences. So if you look at the top here, I have this instruction that's kind of formulated. It's move some 32-bit constant into EAX, and that gets encoded into this 5-byte value. But if we return to the second byte and decode from there, it becomes a different instruction sequence. And it becomes store EAX into ECX plus 8 and then ret. And so the main idea behind ROP is we find these useful instructions followed by a ret, and then we chain them together to build a program. And it's sort of like a ransom note. You go through a newspaper, find the letters that you want, and then write a message using those letters. And I'm kind of breeze through this a little bit. But yeah, and we basically build this all up to build a program. So the defense against this is what's called ASLR. And because like what I mentioned is, like the exploit that we wrote today, we had to hard code a memory address. And when we're doing ROP, we have to hard code a lot of memory addresses. So if we just shuffle those around, we're going to make all these things more difficult because everything that an attacker depends on is going to move around. So ASLR does that. It moves around executable memory, moves around data memory like the stack and the heap, and everything that can be randomized, ASLR will try to randomize. And what attackers will do is find bits of memory that aren't randomized and figure out how you can still use those to gain code execution. And so the ways that you'll do this are sometimes ASLR will have poor entropy, like it won't be very random. And so 50% of the time, something will be somewhere that you know, or 20% of the time, and that might be enough. But what's done more often is memory address disclosure. Other vulnerabilities or other tricks can reveal memory addresses. And if you can reveal a memory address remotely, you can then build that into your exploit and launch the attack. So I think, yeah, that's the last slide. Wait, let me just go this here. And so, for instance, here is a easy ASLR bypass that worked. Oh wait, actually no, this is Vista in IE7. I'll tell you about another one too that was just fixed in Windows 7 like a few months ago. But this one was in IE7. Internet Explorer used to support these things called .NET user controls, which would be a .NET module that would get loaded from a web page. And .NET modules are just PE files. And so what you could do is you could, in PE files, they have a thing called the preferred load address, which is where the executable says, hey, I want to be loaded at this memory address. So you could create a .NET control with a chosen memory, with your own load address, and then when Internet Explorer went to your web page, you could say, hey, load this memory that I have created for you at the location that I've chosen, and with these memory protections. So basically, before you ran your exploit, you could put your payload at a chosen memory address with readable, writable, executable memory. And so you know that it loaded this .NET control and put my payload at 0x200000, and then you run your exploit and then just jump to 200000. Or you could say, I want to make sure my payload is at 0x41414141. You could do that by creating a .NET control that would that the load address and the protections and all that stuff in the PE file would actually tell Internet Explorer to load it there, which was a pretty cool trick. And Microsoft fixed this in IE8 by only downloading .NET user controls from the intranet zone. So they wouldn't load them from the internet, only from the local network. So that's kind of an example of how you get around ASLR. So I think we're kind of ran a little late, but yeah, that's fine. Does anyone have any questions before we? All right. We'll send out the homework. Oh yeah.
I'm sorry. Actually, can you go over what the expectation is for homework?
Sure.
You're going to post it, and what's expected to be handed in?
So the homework is we're going to post an executable, which actually it's the homework.exe that was the homework for the last week, where you're supposed to reverse engineer the binary and find the vulnerability. So it's that same executable, and we just need you to copy it. Well, I'll give you the instructions. You need to copy it onto a certain place in the VM, and then write a small exploit using Ruby. So it'll be a small Ruby program that will print out the right output to exploit the program and get a shell. So just like I did today, I wrote a small program that I could run and send over the network, and then it would exploit the program and give me a shell. The homework should be just that. So basically, for instance, actually what I can send out with the homework is I'll send out my exploit for this one. Basically this file right here, that's basically all I need for your homework. But it would be one that works against the homework.exe that we send out. Because this one works against demo.exe. The one for homework.exe is slightly more tricky. All right, cool, thanks.